Our second and final example using variation of parameters to solve a differential equation. We're going to solve this differential equation. 2y double prime minus 4y prime plus 2y is equal to 2e to the x natural log of x. Now in this form, it's not in the correct form to solve using VOP, variation of parameters, because this coefficient, the constant, they are all constants, coefficients, but this one needs to be a 1. So I need to divide the entire equation by 2. So I'm going to do it rather than rewriting it. I'm just going to divide it all right here. I'm going to get rid of that 2, change the -4 into a -2, change that 2 into a 1, change this 2 into a 1. Now, oops, I don't even need to write that. Now the requirements are satisfied. We can now use the variation of parameters. So, as usual, we need to find the homogeneous solution. M squared minus 2m plus 1 equals 0 would be the characteristic equation. And if we solve that, we would get m minus 1 squared. Set that equal to 0, and we get m is equal to 1 twice. Its multiplicity is 2. So what does that give us for the homogeneous equation? Well, let's see. It's going to give us an e to the 1x, and then this times a constant. And then the next one is, since it's a repeated root, we're going to have to do a constant times x e to the 1x. So we'll get c1 plus c2x, all of that times e to the x. So that's c1 times e to the x, and then c2 x times e to the x. Okay, so that was simple. And by the way, I think I'm going to rewrite that. I don't want the e to the x factored out, so I'm going to have e to the x plus c2x e to the x. So this is going to be our y1 of x. E to the x is y1 of x. X e to the x is our y2 of x. And in the previous video, I didn't mention why we dropped the constants, but that's just the way the theorem states. You do that. You have a constant times a function, so we got rid of the constant, kept the function. We got rid of the constant, kept the function. That's how we define y1 and y2. Let's do like we did last time, and let's compute the Wronskian. As the determinant of this matrix, where we take y1 and y2 as the first row, and the second row is going to be their derivatives. So it would be, let's see, the first times the derivative of the second plus the second times the derivative of the first. Okay, this looks to be a little painful. I'm going to move over to the left a little bit. The determinant. So I'm going to multiply this, then minus that. So I'm going to get x e to the 2x plus e to the 2x. Convince yourself, and let me convince myself that that's right so far. I distributed when I did this times that, and then that times that. So when you add the two exponents of x, you get 2x. Minus. Multiply these two things together, and we get x e to the 2x. So, x e to the 2x minus x e to the 2x goes away, and we get just, for the Wronskian, e to the 2x. I left off for w, I left off the y1, y2, but so our Wronskian is e to the 2x. And I think similar to the last example, I'm going to get you started in the calculus, but I'm going to save that and leave it as a problem for the student. I'm not going to go through all the calculus 1 required. All right, now that we know that, we're going to use the theorem. and it'll tell us that yp is equal to negative e to the x, y1, yep, negative e to the x times the integral of x, e to the x times e to the x ln x, that's our f of x, over the Wronskian, which is e to the 2x dx. Okay, I'm going to write smaller so I can squeeze it in here, plus y2x e to the x times the integral of y1 f of x, which would be e to the x ln x, again, that's f of x, over e to the 2x dx. And all that simplifies greatly. I mean, this is e to the 2x. It just cancels with that. So this is the integral of ln x. And this e to the x will, oh, that's e to the 2x here. So that would cancel with this, and we get the integral of x ln x. So maybe I'll go that far. Negative e to the x times the integral of x ln x dx plus x e to the x integral of ln x dx. So I'm going to show you just the start of how you'll do it by integration by parts. Here we would say u is equal to ln of x, du is 1 over x dx. Over here, and well, let's see, let me get the v. V is 1/2 x squared, dv is x dx. That's for the first integral. For the second integral, we'll let u equal ln x, du equals 1 over x. V is going to be x, and then dv is going to be dx. So after you do all the integration by parts, you get this. Negative 1/2 e to the x, x squared ln x, plus 1/4 x squared e to the x, plus x squared e to the x ln x, minus x squared e to the x. 1, 2, 3, 4. So combining like terms, we get yp is equal to 1/2 x squared e to the x ln x minus 3/4 x squared e to the x. So if you look at the two starred boxes, you can get the final solution is y equals yh plus yp. I'm not going to write it out because I kind of ran out of room. So y is equal to these two terms added together plus this term minus this term.